afternoon, everyone. Today, my talk is about using a sharp-side-based solver to solve quantum circuit compilation tasks. So, by quantum compilation, it involves several questions. So, the first question we have would be quantum circuit synthesis. So, I get a specification of a circuit. It could be a circuit in a higher level gate set, or I get a unitary operation, and I want to get a circuit in an elementary gate set that implement this specification. And this circuit, we have certain specification for this circuit, like I want to minimize some gates in the circuit, and this gate might be very expensive for certain hardware, like T-gate is sometimes expensive for the hardware, so we want to minimize the number of T-gates, or we want to minimize the depth or the space of the circuit. Then, since we have quantum circuit synthesis, the next question would be, I want to check if the circuit I synthesize is equivalent to the circuit I get as input. So we have quantum circuit equivalence checking. And the basic question would be how to do quantum circuit simulation. So I would argue that if we have better methods for quantum circuit simulation, we would also perform better on quantum circuit equivalence checking and quantum circuit synthesis. Yeah, and as we could see here, we already have results published on different papers about these three questions, and the one about quantum circuit synthesis we just recently published in CP conference. And today I will present this tool called Quokka Sharp that can do the tasks I mentioned in the previous slides, and also plus verification, some triple style verification on quantum circuits. And for these four functionalities, we could see that it shares the same procedure here, which is circuit encoder. And I would say that for all this functionality, we will use the same way of encoding, which we'll show later. And then we will do different post-process for different functionalities. And in the end, we will get the output. And for all these three functionalities, they can, including simulation, verification, equivalence checking, it can all reduce to weighted model counting problem. Except for the last one, for the synthesis problem, it will be reduced to an extension of this weighted model counting problem called weighted max sharp set problem. And for this question, in the end, we will get the depth optimal circuit. Okay, so to compare our tool with other tool, we could see that Quokka Sharp can do very broad applications, as we showed before, and then maybe other tools are focused on specific tasks. So let's first recall what is weighted model counting to keep us on the same page. So we are familiar with satisfiability problem, which is finding to check if there exists satisfying assignment for a Boolean formula. And the model counting problem is counting the number of satisfying assignment. So for this case, the model counting of f is 2. And weighted model counting formula, so we define a weight function for a Boolean formula on the variables. And for example, here I define weight function on x, y, and z on the literals. And then I compute the weight of satisfying assignment by multiplying the weight of the literals. And then the weight of the formula, I compute by add the weight of the satisfying assignment. And in this case, it's 1/8. So as we mentioned in the previous slides, the synthesis problem is reduced to an extension of weighted model counting problem, which is called weighted max sharp set. And this problem, for example, here's the definition of this problem. So if we set this read X, this set of variables, to be empty set, we will get exactly the weighted model counting problem. But with this set X, I aim to find an assignment to X such that it can maximize this weighted model counting of formula F. So we define the output of this max sharp set, weighted max sharp set problem as a tuple, including assignment to X that maximize this formula, the weight of this formula, and the maximal value. Okay, so as we mentioned in the structure picture for this figure, we said all these four functionalities share the same idea, same encoding of the quantum circuits. And now we will see how we encode quantum computing in the weighted CNF formula. We start with a simple example. So for these three states, the first type I want to encode it is I encode each term as an assignment of a set of variables. And then I will find a formula such that the satisfying assignment of this formula is the set here. So we could see that for these three cases, I can find a Boolean formula that encode the states. And let's consider a bit more complicated case. We know that superposition is an important phenomenon in quantum computing. So let's consider superposition here. And right now, we just ignore the amplitude. And later, we'll see how to encode amplitude. So for superposition, I will use two satisfying assignments for each basis state. And so in this case, there are two satisfying assignments. And to make it a valid state, I add amplitude here, 1 over square root 2. So I need to keep information of this weight on each basis state. And to encode this weight, we need this weighted model counting. We need to define a weight function on an additional variable h, and we define a weight of h in this way. So we know the weight of h to be 1 over square root 2 when it's false. So I set h is false on this satisfying assignment, and h is false also on this satisfying assignment. So I can get a formula, not h, for representing this state. Okay, so this is the basic idea of how to encode a quantum states. And here I show everything in computational basis. But actually, in our tool, we can also do a density matrix and the Pauli basis. But for this talk, we will focus on the simple case. And we move to quantum gate. So to update the quantum state, we need a quantum gate. And to encode this quantum gate, I want to find a formula, takes variables to encode the input state, x before, and I take the variables for encode the output state, x after, such that I have this formula f x before represents ket per psi, and this formula x before a conjunction between these two formula represents the output state. And let's write it out. We have the Hardeman gate, and then I can compute how Hardeman gate perform on each basis state. I can write out the Boolean formula of each case, and then by combining these two formula, I can get how this H gate will perform on on 1 qubit. So we can do the same procedure for other quantum gates, even for a general unitary operation, and encode it this way. But actually, we can just encode a universal gate set to do universal quantum computing. And now we know how to encode quantum states. We know how to encode quantum gates. So for to encode a quantum circuit, here in this example, we just have to copy the the variables for input for encode quantum states each time step, and then so we only show FH in the last slides, but we can also do FC0 and FT using the same method. And here, we just do a conjunction of all the formulas, and then we get this big formula, and then the satisfying assignment of this formula can be interpreted as the output state here. So until now, we didn't do counting yet, and so now we move to the applications of this encoding. So with the current encoding, we can do simulation, verification, equivalence checking, synthesis. And for simulation, I defined the question as this. So we have the input circuit, input state circuit, and then we get amplitude of a certain basis state. So we get a measurement. We do a measurement in the end, and in the formula, it would be based on the encoding we showed in the previous slides, and then we would add the encoding of the output state in the end on the output variables. And by computing the model counting of this formula, we'll get the amplitude of this basis state. And we consider a triple step verification, and the problem would be if we start with a certain projector, we can encode a general projector using our encoding. And after the circuit, we want the output state to be in a certain projector, and we can also encode a projector in the output state. And the use case for this verification problem would be like quantum circuits include some ancillar qubits, and we want this ancillar qubit start with 0 and end with 0. So in this case, for example, we want to ensure that the first qubit start with 0 and end with 0. So the encoding formula would just be I force the variables for encoding the input state to be not x0, and in output state variable for x3 to be not x3. So now we move to equivalence checking. It's a harder problem compared to a simulation verification. And now we are here. We will not go into the details, but our results show that if given two circuits, U and V, we can encode it. We can encode FU, use the method we showed before, and we can encode V dagger. So we get so to check the equivalence between U and V, instead we check the equivalence between UV dagger and identity circuit. And after computing this encoding, the weighted model counting of this Boolean formula, we will get the Jamiołkowski fidelity. So since we can get this fidelity out of this formula, we can determine the approximate equivalence checking of these two circuits. And if we set this epsilon to be 0, then we can decide the exact equivalence of these two circuits. OK, so the synthesis problem is, as we said before, we need to get a circuit that's equivalent to the specification. So here we solve this question by by encoding all the possible gate layers. And after encoding all the possible gate layers, we will choose between these possible gate layers, and which is using these variables in this red variable set P. So we find assignment to this variable P, and then we can decide which gate layer here in S. And if we cannot find this kind of gate that's equivalent to this input U, I will add another layer until I found a solution that's equivalent to the input. So as soon as we find the solution, we can get a depth optimal circuit. So to wrap it up, so we present this tool, Quokka Sharp, that can encode quantum circuits into Boolean formulas. And this encoding is linear to the number of gates and layers. It's also linear to the qubits for simulation, verification, equivalence checking, but it's polynomial to the number of qubits in synthesis problem. And it has these 4 features we have talked about. And here we show that this problem, all these 3 problems can be reduced to weighted model counting, and the last problem can be reduced to a max weighted model counting. And the tool is currently online, so you can find it in this GitHub called Quokka Sharp. You can just search it in Google, and then you can try and play with it. Yeah, and that's my talk. Thank you.
Yes, thank you very much. And are there questions?
Hi, thank you. For the simulation part, how hard would it be to extend this to also do sampling or like expectation value of some observable? Because you could only kind of do like sample one amplitude of one kind of state, right?
Yeah, thank you for your question. So here I show the example of only sample one basis state, but you can also do like this output measurement can be just a general projection, and that's also possible. But for a weighted model counting problem, every time you just get one result out of the solver. So if I want to, so it's not possible that I get a sampling of the whole vector. But like we already showed that just with this measurements, we can already do like equivalence checking, synthesis, different tasks. So I would argue that this kind of the definition of this simulation is already canonical.
Hi, and thanks for talk. And I'm interested in the verification part, and I was wondering whether the weighted model counting method could be used to encode the general Hermitian operators, okay, for these predicates P and Q, and since the Hermitian operators could be used, could be decomposed into the linear combinations of projectors, okay, and is there any difficulties? Yeah.
So let me maybe rephrase the question a bit. So are you asking that I can make this P and Q to be a general Hermitian operator?
Yes.
Yeah, I would say it's possible to do that because we showed that we can encode this Hermitian Hartmark gate by encoding this matrix. So actually, our encoding supports a general matrix. So you can just use this weight function to define each entries of the matrix. So in this case, you can encode. You can make this encoding very general. Thank you for your question.
Thank you for the talk. I'm wondering whether you could do something like symbolic execution as is done in Kubrick's, or is it possible?
Sorry?
Is it possible to do something like symbolic execution as done in Kubrick's? Like you would have some symbolic variables and you would reason over them?
Like you do symbolic execution, but what would be the specific?
Suppose you start in some the zero basis as an amplitude x, like some variable. So could you get some as a result of the simulation some expression over x?
Yeah, that's a very good question. So for the current tool, we cannot we don't support that because like we are not supporting symbolic execution, but now, like, we are collaborating with also weighted model counting community, and they are providing this symbolic weighted model counter, and with that, I think it's a very good future work that we can do.
Okay, thank you.
So thank you. Let's thank the speaker one more time.